right now. I am asked to determine the electric field intensity along the z-axis due to a flat disk of radius A and uniform surface charge density that is lying in the xy plane. And then I need to take a look at the limit of that result as the observation point H, so that being the height on the z-axis, gets much larger or much smaller than the radius of the disk, and then interpret what that is supposed to mean. You can take a screenshot of this example, or you can follow along in your book. It's on page, it starts on page 54. So I'm going to switch over to my document camera now and walk through the steps for solving this problem. Here we go. So I'm going to start by drawing a diagram of this problem. And it's going to look like this. I have my coordinate system. I don't think I've ever solved a problem without drawing a coordinate system. That's almost always the thing that you should do first. And inside my coordinate system, I have a disk that lies within the XY plane, that being my x-axis and that being my y-axis, so that x cross y can be z as usual. And on my disk, which has radius A, there we go. I have a uniform surface charge density. So I'm just going to write down rho s constant. So far, so good. Now I would like to determine the electric field intensity on the z-axis due to this disk. To do that, I think I might actually like to draw that picture a little bigger, because I'm going to make a symmetry argument first. So a bigger version of that image is going to look like that, like that. Here's my disk. I have an observation point that is going to be somewhere on the z-axis. So that height is going to be h. And if I want to know the differential electric field due to some part of that rho s on my surface density, the first thing I need to know is that the electric field, I'm going to write the differential electric field element, is going to be dq over 4 pi epsilon naught big R squared. Remember that R squared, that R is the distance from my differential charge to the observation point. And then I'm going to have an A hat R. So the direction of A hat R and the value of R are both going to change as I go through this integral and vary my variables. I'm going to be varying both rho and phi, because I'm probably going to do this in cylindrical coordinates. And I'm going to vary those over the surface of the disk. So if I'm working in cylindrical coordinates and I'm doing a surface integral over the surface of a circle or a disk, what I'm going to do is try and figure out what are the dimensions of my differential surface element. I'm going to vary over rho and phi. When I vary something over rho, that means that my differential length element along rho is just going to be d rho. Cool, easy peasy. When I vary along phi, remember phi doesn't have dimensions of length. So if I choose a point on the circle that's like here, and I vary along phi by some angle d phi, the length of this distance that I move is not d phi, because d phi has no length. It is whatever radius this point is at times d phi. So that's rho d phi. The product of these two is going to make my differential surface element, which means that dq is going to exist on a little slice of my circle that kind of looks like this, whose dimensions are d rho and rho d phi. So that little guy is dq. The value of r, and dq obviously can move around because I need to cover the entire surface of this disk with dq's. That can move around, and the value of big R up here in this equation is, oh, can I draw a straight line? The distance from my observation point to dq. So that is big R. And I'm going to draw a hat R up here. That's a hat R. I'm drawing a hat R up there because the electric field is acting at this location. So it's in this direction, and the location that the field exists is over here. Here comes the symmetry argument. Check this out. The differential electric field component due to this dq has a z component, but it also has a radial component, right? It has some rho component away from the z-axis. It doesn't really have a phi component because there's no component that is circulating around. There's nothing that's going to the side, but it is going away from the z-axis along here. However, the total electric field we're going to find due to this disk on the z-axis will not have a radially directed component, because for any dq, this is the symmetry argument. Whenever I say for any dq, I can choose another dq. That's the beginning of symmetry. So for any dq on this side, I can choose another dq on the other side of this of the disk over here. I'm going to name that one dq prime. That will have an equal magnitude of dE, but an opposite radial component of a hat r. So I'm going to name that a hat r prime. You can see how their z components are going to add up because they point in the same direction, but their rho components point in opposite directions, so they will cancel. That's how you make a symmetry argument. I can choose another dq for any dq, and then I can cancel out some vector component. So what I'm saying here is that we only need to care about the z component of that unit vector. What is the z component of that unit vector? Let's do some triangles. A hat r is going to be similar to, in fact, I'm not even going to write down an equation. I'm going to draw a triangle first. We have our z-axis here. This distance is rho. This distance is h. And this big, you see the whole triangle I'm drawing? There we go. The whole thing is r. dq is over here on this corner. And p is up here at the top. Where is a hat r? It's right there. And its rho component is like that, and its z component is like that. So I'm gonna name that as a hat. I'm gonna name that as, well, it's just the z component. Let's find out the value of this, right? So, oh, I can write it as the dot product, a hat r dot z hat or a hat z to have consistent nomenclature here, and a hat r dot a hat rho are those two lengths. The length of a hat r is 1 because it's a unit vector. Cool. So the length of a hat r dot a hat z is going to be the same as the same ratio. So I can write that, need a little more space at the bottom, a hat r dot a hat z over 1 is equal to h over big R. What's the value of big R? This is a right triangle, obviously, because the z-axis is perpendicular to rho. So the value of big R is, I'll just replace it, square root of h squared plus rho squared.
Professor, could you angle the camera a little bit more upward so I could just
Oh, you need to do the tiny triangle again?
Yeah, the tiny triangle. Thank you.
Okay. We're looking right here at the vertical part of the tiny triangle. So far, so good?
Yes.
All right, great.
Thank you.
So now I need to erase a lot of stuff because I'm going to write down the integral. Keeping dE for a moment here. And I'm keeping this stuff over here about the triangle because I need that for a second. And I'm going to write that the total electric field at some location 0, 0, h, because that's the only thing that we're asked to solve. We're not finding it anywhere other than the z-axis. It's a vector. It's going to be z-directed because of my symmetry argument. So I'm going to write a hat z right here at the beginning. All we got to do. And then we have to integrate over the area of that disk. We're going to go over the values of phi from 0 to 2 pi because it is a circle, not part of a circle. So we have to do all of the possible values of phi. We're going to go over the values of rho from 0 to a, because a is the radius of the disk. And then we've got to do dq. So dq is actually the surface charge density times rho d phi, right there, divided by 4 pi epsilon naught. Value of r squared is h squared plus rho squared. And now we need just the z component of a hat r, which we found over here under the big triangle. See that? So at the end over here, I'm going to write h divided by the square root. So I could write down the square root, or I could just make this be to the 3/2. All right, this is my integral setup. Because we don't care about the z component. Now, most of this stuff is constant with respect to the variables that we're integrating with. So I'm going to factor out a bunch of stuff. And I'm going to notice that nothing here depends on phi. So I'm going to evaluate that phi integral from 0 to 2 pi and gain a factor of 2 pi. So what I end up with, there you should be able to see everything now, is going to equal a hat z, still very important. 2 pi that we gain from the phi integral divided by 4 pi is just going to be a factor of 1/2. So there on the bottom, we're going to have 2 epsilon naught. And on the top, we're going to have a rho s, and we're going to have an h on the top.
Professor, what value is equal to that equation that you're writing out now?
The integral.
Oh, okay. My bad. I thought you had a factor on the outside.
Yeah, this stuff that is, I'm moving all of the constant stuff outside of the integral and evaluating the integral with respect to phi, because we have nothing that depends on it. So all of the things that I've circled up here are going into this stuff, and I'm doing some simplifying. Because when you evaluate this d phi integral, you get a factor of 2 pi, and that cancels with the 4 pi, so it's just 1/2. So I have rho s h over 2 epsilon naught. That's what I got here. So far, so good? Okay. Then we have some more complicated stuff, because what we have left is an integral from 0 to a of rho over h squared plus rho squared to the 3/2 d rho. This is not an integral that is easy to evaluate just by remembering what it is, what its value is, or by applying the various rules. You can also do like a trigonometric substitution, which is the way that I usually solve this. But you can also, all right, so there are a few different ways of evaluating this. I'm going to write down your options, and then I'm going to say that luckily we can also just look up the answer to this integral. But trig substitution is a good one. That's a really good strategy because, as you know, this integral came from a triangle. So if you turn it back into a triangle form, this actually turns out to be, you can express it in terms of sines and cosines and tangents and stuff. So you can always do that. Trig substitution is good. You can also represent it as polynomials, like polynomial ratios, and deal with it that way. But the third option is look it up. So that's what we're going to do. And if we do look it up, we get that, let's scoot down so you can see what I write at the bottom here. This is equal to, still have a hat z, surface charge density times h over 2 epsilon naught. And then this stuff is going to be 1 minus h over a squared plus h squared square root. That's it. Cool. Actually, I'm going to go back one step, so I'm going to write it down in its, my apologies. You're all taking notes, and I'm sorry. Can I finish my sentence first, and then I'll answer the question? This stuff is -1 over square root of rho squared plus h squared evaluated from 0 to a. Yes?
Would it make a difference if we just did the integral in terms of the magnitude of the vector field, since we know all the rest of the components are 0 except for in the direction of k hat or in the direction of z?
Yeah, the only difference would be that this a hat z vector that I'm writing at the beginning right here wouldn't exist, and your result would not have an arrow on top. It would be, you would write down e sub z to denote the z component of e, and then it would look like that. E sub z equals that, and then you would just write down that the other components of e are 0.
Okay.
So I can leave it in this form and just continue doing the same thing. When I do this, the result then is rho s h over 2 epsilon naught, cool, times 1 minus h over square root of a squared plus h squared. And that is the z component of the electric field on the z-axis due to that disk of charge that we drew at the beginning. The interesting thing to note here is if you take a look at what happens when h is much smaller than a. So that would be when you are right on top of the disk. I'm going to erase some stuff and draw a picture of this. If you have the disk here and you are a very short distance above it, that's H maybe, then the value of this electric field is approximately just rho s times H over 2 epsilon naught. You don't know that yet. You don't know this yet, but that value is, there now you can see everything I'm talking about. That is also the electric field due to an infinitely large planar sheet of charge, which makes sense. If you're that close to the disk, you can't see the edges. On the other hand, if you move really far away, if you're like, go up really high off the board, and that value is H, then you end up with what do I get? Basically 0. Because you get 1 minus H over H, and you get 0 field. Which makes sense. You're sort of infinitely far away, and so you're far enough that there is no appreciable field due to this thing. All right, it's 11:04. I don't expect you to be fully able to solve your example of the same thing, but I want you to try.